Section 9.1 in chapter 9 is called voltage induced in a coil. And so what we're going to look at is the basic building block of a transformer. We're really kind of looking just at one side of it. And then all we're going to do is bring two coils in proximity to each other. And we're going to sort of create this transformer one half at a time. So when we look at this idea of voltage induced in a coil, we're going to look at a particular figure, figure 9.1, and our first equation for chapter 9. So let's look at that and work through this. So as we begin this thought process of how a transformer works, I want you to look at figure 9.1, and I want you to look at part A here. And I want you to imagine that this is a coil. A coil is simply, a conductor wire wrapped around some ferromagnetic material. And that internal to this coil is a changing magnetic flux, okay? And it's represented here, right? And I want you to understand that this flux is varying sinusoidally. It has positive and negative peaks, and again, this coil surrounds this changing flux. Okay, so what we can do is we can quantify this, and we can write our equation 9.1 that says that the voltage induced in the coil, and that's not looking real good. Let's see here. Let's maybe take a bigger mark here. It says the voltage induced in the coil is equal to 4.44, and we'll see where that number comes from in just a second, times the frequency, times the number of turns, times the flux. And this is actually peak flux, and we'll actually come up with the reasons why we use peak flux in not something else in just a second. And one thing very important, I want you to get this is an effective voltage, okay? Effective, we think RMS, right? So this is an effective voltage. This is the frequency of the flux. This is the number of turns in the coil. This is the peak flux in Webers. And this is a constant that, again, we like these constants that we don't have to derive, right? It actually is 2 pi divided by the square root of 2. Now, we could probably get there pretty easy, but we don't have to, just a short skinny on it, it's a way that we deal with an effective voltage, right? We know the relationship with square root of 2 and so forth and so on. Now, he tells us in this section that it doesn't matter where this flux is coming from. It could be created by moving a magnet, or it could be from a nearby coil itself, or it could even be the AC current that's flowing in this same coil. It doesn't really matter, and that's not a critical part of this. But we just want to realize that this flux and this coil are interrelated, and that, they, in this particular case, the coil surrounds the flux and it's varying. And so what we're looking at, and let's look at this in terms of a graph. Here is this varying flux, right? That's going like this. And here's the induced voltage that is accompanying that. Now, first thing that might jump out at you there is that when we're at this point, we're at the 0 point, and we see our flux, our induced voltage, excuse me, our flux is 0 and our induced voltage is maximum. And then here, our flux is 0, excuse me, I just can't get this right. Our voltage is 0 and our flux is maximum. And so what we're dealing with is the idea that when we think of, if you'll remember, inductors, right? The voltage leads the current by 90 degrees. And so we'll talk about how that fits this in just a second. All right, so that's our fundamental. This is our starting point. So Wilde tells us with this equation 9.1, it's actually derived from Faraday's law that is given by this equation, but the voltage is equal to the number of turns times the change in flux over the change in time. So really what you're looking at, if you pull this out, you know, this is set, right? That's a number of turns, but this is a rate, you know, this is the rate. So if you're having a very large amount of change of flux in a very small amount of time, then you're going to have a very large voltage. And so, you know, the greater the rate of change, the faster this is happening, this instantaneous little e voltage is going to be larger. He goes on to say, if the rate of change is positive, you know, if it's greater than 0, the voltage would be positive, you know, during that time. And you can look at this, you know, you can look at this in terms of this curve here, and we can observe the voltage along with it. And so anytime that the rate of change is positive, anytime the rate of change is positive, the voltage is positive. Now, you know, we're not in a math class, but you're probably taking your calculus courses now, right? And if we looked at that part of the curve at this point and beyond, going in this direction, right? If I'm going down this direction here, the flux is decreasing. And what do we notice? What we notice here as the flux decreases, the voltage becomes negative, okay? So, you know, you can just sort of track this along the curve and see the interrelationship of that. And this isn't some sort of pep talk for mathematics, but, you know, with just some real basics of calculus, you can, you know, do this differentiation and determine values. But that's something that's coming to you as you proceed through this. Right now, we're doing it more graphically, and I think you probably get a better feel for it because of that. But, you know, as long as the flux is increasing, the voltage is positive. And when it decreases, the voltage becomes negative. So, you know, we're producing this sine wave over time of this voltage output. You know, when it's not increasing or decreasing, right? You know, at these points, you know, the voltage is 0 at that point. And anyway, so just pointing that out and try to give you some feeling for why you do actually study this higher mathematics as you proceed, but that's not in this class. You'll get there. And then the last thing in here, he says, question arises, why do we use peak flux instead of RMS value when we're getting an RMS voltage? The reason for that is that the peak flux is proportional to the peak flux density. Okay, so let me try to put that in my words. What that means is if I'm using peak flux, that is an actual value that we can use. Now, it's proportional to the flux density, but in the curves that we look at, we know that the material can saturate. And so to get some type of accuracy with this, you know, we could be anywhere in that saturation curve. So, you know, we don't want to do that. We need a place here that is one value that we can use. And so, you know, for that reason, that's why this equation uses peak flux. Now, let's look at a little simple problem and we'll be done with this section. And we'll just apply this equation 9.1. And this is one of those plug and go kind of problems right here. Okay, let me give us a little more space on here. All right, and it says, this is example 9.1. It says I have a coil, or this coil in particular. It has 4,000 turns. Okay, so that's equal to N. And it links an AC flux that has a peak value of 2 milliwebers. Okay, so that is this, and it's a peak. And the frequency is 60 hertz. Okay, and that equals F. And he says, can you tell me what the effective value and the frequency of the induced voltage is going to be? Well, I can tell you right now, if the flux is at 60 hertz, the induced voltage will reflect that same value. So, you know, we already know that, so that's not something that we have to calculate. The rest of this is simply a plugging in. So to calculate what that induced voltage is, it's 4.44, which is that constant. That's 2 pi divided by square root of 2. The frequency is 60 hertz. The number of turns is 4,000. And the peak flux is 2 milliwebers. We plug all this into our calculators, and we come out with 2,131 volts. We know this equation is effective value, or RMS value. And so, you know, there's nothing else to do with that. The other thing that he actually does in this problem, he says, what would the peak value of the voltage be? You know, what would these peak values be for the voltage that we're working with? Well, we know how to do that. We've got 2,131 volts RMS, and we want to convert that to a peak value. Then all that we have to do is multiply that by the square root of 2. And when we do, we're going to end up with 3,014 volts peak. Okay, that's section 9.1.